Hello everybody, and thank you for joining us for this Autodesk CFD webinar. Today we'll be diving into the Solve dialog and having a look at solution modes. That is transient and steady state solving. This can sometimes be a little bit tricky to get your head around, but luckily we have Matt with us here today to help us out with our understanding. Matt supports CFD from the Americas, and I'm sure many of you already know him, but Matt, if you'd like to say hello.
Hey, thanks for the introduction, David. Yeah, we just are going over steady state versus transient, when to use which one, and advantages and disadvantages.
Nice. And yep, I am David, and I support CFD out of our Munich office. And we'll be running through the basics of solution modes before we jump into some demos. So I hope everyone can see my screen. So today we're going to look at, firstly, a brief explanation of steady state and transient solution modes. Then jumping forward into the main concepts of, so the most important things when you're setting up a transient simulation. And we're also going to discuss the possibility of combining modes. So in one simulation, you can do both a steady state and a transient analysis. And we'll run you through where this could be appropriate and where not. I've got some examples. We've got one example, an animation of a transient flow, and then we're going to run through some demos. And we have a bit of a theme for you here today, as we've only just realized we've done similar simulations, but I don't know, we've got good things to share on both. So I'm doing jacket potatoes in an oven, and Matt is doing roast turkey. So we'll see how that goes. Right, so the basics of steady state solving. What we're looking at is simulating constant flow and heat transfer regimes. So this is only valid in a simulation where the physics itself is steady state, so a steady flow phenomenon. And for this, you also need, so even if you do have a steady state flow phenomenon, you still need constant boundary conditions and a constant device behavior for it to be a valid steady state simulation. And one nice way of looking at it is, like, if you take a picture, that should describe the flow completely. And if you waited another 10 seconds, took another picture, there would be absolutely no difference. And this is a lot less computationally intensive than a transient solution, which is, sometimes you can think of it as at each time step, you're doing a small steady state analysis.
Awesome.
And so a really good example of this is when we're looking at flow around a cylinder. And if you're looking at flow at Reynolds number less than, I don't know, really small, so around 10, you're going to get a constant flow regime round the cylinder, as you can see by this picture here. Whereas for higher Reynolds numbers, we're definitely getting into a transient behavior where the physics itself is transient.
Yep. And David, just one note there. Sometimes you will see, people will come to me and ask, I just ran a steady state simulation. Why is it never converged? And that's because there are, by definition, transient behaviors in it. If there's usually it's some kind of like vortex shedding. I saw this recently in a valve where basically there's really unsteady behavior, and you just have to understand. You're going to see probably the velocity terms. It's not going to be pressure, but the velocity residuals are going to oscillate constantly. Now, it's still okay sometimes to run, a steady state analysis because that snapshot is good enough, basically. And then other times it's not. A while back, I did drag over a cylinder that was by definition transient. We knew it was. We were looking at the drag, and we were able to determine that the characteristic drag within a reasonable amount of certainty could be, snapshotted in a steady state analysis. It was not perfect, but it was pretty good for what we needed there.
Yeah, absolutely. So on to transient solving. So when we need transient solving, we are simulating a time-varying flow or heat transfer. This is an iterative process at each time step. So I'm sure many of you have seen in the solver dialog, when you select transient, you get the option for inner iterations. And these can sometimes be considered like a steady state iteration. However, you're doing it at each time step. And it's in a transient simulation, what you're doing is you're continuously iterating at the current time step until, if you give enough inner iterations, until you are calculating all the different flow parameters with the flow parameters at the current time step, rather than an explicit method where you would be using all the flow parameters from the previous time step. And we jump to the next time step once we've reached convergence with these inner iterations, and then the solution to the flow parameters at the current time step then becomes the old time step solution for the next time step, and then we're iterating again.
Awesome.
And a nice comparison with a steady state solution is that we can think of it as an infinite transient solution to a problem with constant boundary conditions. And we're actually going to hopefully show this with our oven simulations later.
Right, exactly.
Actually, no, we don't really get very close, but but we'll give you the idea.
Awesome. Yeah, just to touch on those a little bit again. A lot of times people ask me, how many inner iterations do I need to use? And that, there's no perfect rule of thumb. We default to 10, but that tends to be overkill. So as I'm running a simulation, I look at the inner iteration terms and look at the residuals for the pressure, velocities, temperature, and so on, and I see if they vary inner iteration to inner iteration. If they just are flat the same, basically, it means I'm wasting time. I mean, it's good to be sure. If you run one, you never know, and two can be a little sketchy if you get two different numbers. So honestly, I usually go with three and then see if they're changing much. If you get the same residuals, it's a very good sign. If not, you should probably up the amount of inner iterations. And yeah, just like David said, a steady state solution is an infinite, transient solution. When I run transient simulations, the first thing I do, almost no matter what, is always run a steady state first, because I just need to get some kind of understanding of my field variables. Even if I just need to know, okay, what's the characteristic velocities, because I don't even know how to decide on a time step. I have no idea. Run a steady state, start doing some hand calculations, and go from there.
So to give you a little summary of when we think transient solving is necessary. So the first point is when the CFD user actually wishes to examine a result parameter varying in time. So this is you could be getting to a steady state, but you still want to see your flow parameters varying with time. So common examples of when this is useful is when we're looking at motion, because you don't want to just run to infinite to see the steady state motion. You really want to, well, in most cases, you want to be seeing that motion over a predefined time scale. This is the same for rotating regions, whereas in rotating regions, we look at it as a time step per certain number of degrees of rotation. So we're not really worrying about the steady state solution at the end. We want to see how this thing is ramping up over time and how the flow is developing over time. Same with free surface analyses. You can get some free surface phenomenon that reaches steady state, but it's very unlikely because there's so much randomness with free surface, and it's much more it's much more interesting and valid to look at it changing over time, because that's where you're actually interested in, and that's what you would be doing with an experiment to compare with. Again, with
sorry for interrupting, David.
Yeah, sure, go. No, go for it.
The free surface analysis, we couldn't, if we wanted to, come up, deal with the time step term in a steady state manner. There's no way we could solve this, the theoretical background there without keeping the time term in the solver. So yeah, like David said, sometimes you might have to run out until you hit steady state, but we would never get there without the ramp up in the beginning.
Mm-hmm. Another really important one is solar radiation. So, I mean, you're not that interested in the overall solar radiation because you're normally looking over the time span of a day or something. You don't want to go to infinite and see what that solar radiation would be producing on your building, say, for example. You want to see per hour what the effect of solar radiation on a building would be. So we always do this transiently. And again, with heat up and cool down analyses, these, by definition, you want to see the speed at which something heats up and cools down, and for that you're going to need a timescale to define it by. Some flow regimes, like we've just seen in the first few slides, actually produce transient behavior in nature. So, as we'll take the same example, if you're looking at flow behind a cylinder or over a cylinder at a higher Reynolds number, you're going to get induced vortex shedding. And no matter where you are in that simulation, if you're looking at it in time, it's going to be constantly changing in time as those vortexes are shed behind the body. And this is even with constant boundary conditions, but it's the physics itself of the flow separation that is making it transiently. I couldn't think of any other good examples of this, but I'm sure there are some out there of actually physical transient flow.
Probably cavitation, or really any other kind of valve simulation, but it's the same. It's really just adverse pressure gradients that are creating swirl.
Yeah, exactly. And anything where sort of turbulence is dominating in a way, and flow separation is the key driver of the flow.
Yep.
So, and also, even if you've got a constant flow, a steady state flow regime, you may add non-constant boundary conditions. So say it's just a simple room with a flow going through it, you may actually vary the speed at the inlet. So this is then making it a transient flow. And also you get the same phenomenon with device control. So say if you put a thermostat on a fan, this is going to then change the behavior of the fan through the simulation, and you're going to need a time scale to see this in your analysis. So now we're getting more into the key points of setting up a transient simulation. Probably the most important thing that we're looking at is the time step size when we're thinking directly about transient solutions. So this needs to be small enough to resolve the flow. And by that, it means it's got to be small enough so you capture all the detail in the flow. If your time step's too big, you're going to be jumping from one point to the other, and you're going to miss the flow if it had changed between those two jumps, if you know what I mean. So then you're going to get a completely non-physical flow. And what we like to say is, if you've got flow going over a device, then we like to put a time step size of the equivalent time it takes to traverse 1/20th of that device length, or the characteristic length. And on the other hand, if we're looking at rotating regions where the rotation itself is driving the flow, then we want to look at our default now, or maybe not our default, but our recommendation of best practice with rotating regions is we go for a time step that's equivalent to 3 degrees of rotation. And that should be that should be small enough to really see all the detail in the flow, and you're not missing things between those time steps. On the other hand, if you're looking at heat transfer, you can normally go for a much bigger time step, because the complexity of the heat varying over time it's not jagged, it's not happening super quickly, it's normally a slow process, and you should be able to resolve that with bigger time steps.
David, I like all that. Let me touch on a couple things here. I really like the fact that you say characteristic length, which is interesting. A lot of times that's not your domain, so it could be, but for example, About a year ago, I was helping someone who was looking at the vortex shedding frequency on a nozzle for an oil and gas application. Basically, the vortex shedding couldn't induce a frequency that was within a certain range of the natural frequency of this nozzle. It was just basically a metal pipe. In that case, the characteristic length is not the length of the domain or anything like that. It's what I would argue the diameter of the nozzle, which was extremely small. And 1/20th is a great rule of thumb, but when I'm trying to get vortex shedding over a diameter on a nozzle, I think I went down to like 1/100th or something, because you need a lot of time shots. I mean, you could think about this as filming and how many frames per second you need. It's a very similar analogy. You need to be.
That's a great analogy.
It really needs to look fluid, and you need to be able to follow the flow. And if you can't make perfect sense of it, there's no way the solver is going to be able to. So, and I think on the nozzle application, I went from steady state flow to transient, which is a cool trick, because the startup, or at the very least, use a coarser time step, or else the ramp up time would take a very long time. I basically had a nozzle inside a wind tunnel, so just having the flow approach the nozzle would take a long time. But and just touching on the 3 degrees per time step, that's an awesome rule of thumb. We usually find it good enough. A lot of times with pumps, we're trying to get accurate pressure drops that are within 10%. Some people that do this, all day and night, I've talked to them and they use 1 degree per time step, even half a degree per time step. Some people calculate, that all this is really based on the CFL number. A lot of people, chase that and really check. But, I always like to say you need a time step that's small enough to not affect your solution. And that's always what I aim for. But no finer, right? And with heat transfer, Dave was mentioning there, I mean, that's either with frozen flow fields or with pure conduction models. You can use huge time steps on the magnitude of 30, 60 seconds. But if you have a natural convection model, in other words, if you're modeling buoyancy, basically each iteration you're modeling heat transfer and flow, then you have to go extremely coarse or extremely fine, because you need to adhere to the our rules of thumb when it comes to flow.
You've got to resolve to the most complex thing in your simulation. So if it's natural convection, it's the flow itself. It's not the heat transfer.
Yeah, exactly. I mean, some people say, come to me and say, I need to model, natural convection over a day, and there's really no shot you can do that. A lot of natural convections, 30 inches per second. Your device is less than 5 inches long. You need a pretty small time step.
Yeah, absolutely. And when you look at it on the other side, then you look at a solar radiation analysis where you've frozen the flow, and people can use huge time steps to then really see the behavior over an entire day.
Yeah, absolutely. Like our ovens, I checked my velocity. They're forced convection. It's the most dominant thing, and that's the first thing I checked on my steady state model, because I didn't know if I could get away with modeling it as a frozen flow field. But anyway, sorry for going on a rant there.
No, it's good stuff. So on to inner iterations. As we've actually kind of covered this in the previous slides, but what we're doing there is you're letting the solution converge and become to get to the end of its implicit iterative process. So more with complex flows where there's quite a lot of instability, you might need a few more inner iterations just to ensure that you're getting accuracy at each time step. But I think we've covered that. So on to save intervals. Now, the only purpose of save intervals is for in post-processing. So when we're actually visualizing our transient flows and heat transfer, we have to predefine where we want to save this, because if you save at every time step, you're going to have a ginormous folder. So my roast potato or jacket potato transient simulation that I've just done ended up as 55 gigabytes. I had to delete some folders in there, and that's not with that many saved intervals. But some customers sometimes come and say, no, I want to save every time step, but it's not possible unless you've got a mammoth hard drive and don't mind waiting for hours for things to load. But so when we're looking at it in the solve dialog, you want to think about the total time you want to run, and then split it into the sections at which you want to visualize the flow pattern. Does that cover it, Matt?
Yeah, awesome. It really depends project to project. I mean, honestly, a lot of times I run for one iteration, I get my res file, which sits in the solver folder, and then I go look at the size of it and say, okay, I can afford to do like 40 or 50 of those, or maybe I can only do 10 of those if it's a huge model. I honestly, it's all over the place, but we usually say 20 to 40 save intervals. If your project gets up over 100 gigabytes, it's going to be not a lot of fun to work with.
Yeah, absolutely. Oh, sorry. We good?
Yeah, I'm all set.
So on to the next important thing about transient solving is a lot of the time we want to define the initial conditions for the problem, because unlike in a steady state analysis where it doesn't really matter what you start with, it's always going to reach the steady state solution. With the transient solution, it's important to try and get an accurate starting point such that the results of the initial time steps, so the first few time steps, is actually accurate to reality. So because you need to let your domain initialize and the physics to actually develop. Whereas if you start everything with the default at 0, the first time step results are likely going to be nonsense because the solver hasn't had enough time to converge and to actually resolve the boundary conditions and the physics in the domain. So as I said, with the default values, normally, well, always with the default, the velocity in the domain is set at a 0 magnitude, and the temperature and the pressure are set to the scenario environment that is by default, I think it's 19 degrees Celsius, and I can't remember, atmospheric pressure.
Yeah, 101,
yeah, exactly.
101 kPa.
Mm-hmm. And obviously, yeah, this can improve your accuracy at your initial time steps, and that's the most. That's what they're for. If you want to take a different approach, you could do both, but it doesn't make so much sense. If you want to ramp up your simulation domain, so basically section off the first few time steps, or 50 or 100 time steps, to let your simulation domain ramp up to initialize the flow, initialize the devices, so get them up to their operating state in a sort of steady manner, rather than, and this kind of helps with stability, rather than just going, okay, suddenly everything's on. We're going from 0 initial condition to everything on. The solver doesn't really know what's going on and everything crashes. So this is a nice smooth way of getting into your transient solution, or simulation, sorry.
Awesome, David. Yeah, one point, you mentioned device output, which is a great example. So although I don't love to use it, sometimes people will basically have a induced flow pump model, rotating region model. So they'll have a pressure boundary condition on the inlet and the outlet. Now, if you're trying to do a free flow through a device, you'll have 0 pressure on each side, and it can take a really long time for the simulation to figure out which way the flow is actually going and start to head in the right direction. So sometimes we use a real spike at a high pressure on the inlet side to force the flow in the right direction, and then after whatever, maybe 50 iterations, maybe less, drop it back down to 0, and then we get the steady state.
Mm-hmm. I think this is the last important point about setting up a transient simulation, but it is an important one to cover because it can vary between different types of transient simulations and how we should use it best, and that is intelligent solution control. So there's the little checkbox in your solve dialog, and it's important to know what that is doing, or at least roughly. So with a transient simulation, it will change the time step, and it does this to try and improve the stability throughout the simulation. Unlike with steady state analyses, it will change the relaxation parameters. In a transient simulation, the relaxation parameters are held constant and only the time step is changed. Now, there are some simulations where this is okay when it doesn't matter so much if you don't have a constant time step. But for those that you do want a constant time step, you need to disable the intelligent solution control. So that is for when it's user prescribed motion, so if you've prescribed your motion, you want it to vary with a specific time step, and mainly for visualization purposes, but also with user prescribed motion, it's normally a fairly stable simulation, and it won't need the intelligent solution control to help with the stability. If it does, you just drop if it's fairly unstable, you can just drop the time step size, but keep it constant. When we want to enable the intelligent solution control, this could be for things like flow-driven motion and free surfaces. Free surfaces and flow-driven motion are big ones where there's quite a lot of instability, and there's some real complex stuff going on in the simulation, and the solver needs as much help as it can to stay stable, and it does this by changing the time step. Also, for all of these, I can't think of many transient simulations, or any, where you would keep the automatic convergent assessment on. So just be careful when you enable intelligent solution control, make sure you turn off automatic convergence assessment, because the automatic convergence assessment will stop your simulation early if you have it enabled, because it might think it's reached a steady state at a certain time step, whereas actually you want to see much more than to that time step. And that can be really annoying. So you come back in the morning and you realize that automatic convergence assessment has turned off your transient simulation. So that's a heads up.
Yeah, awesome. Couple points here. Sometimes folks accidentally leave intelligent solution control on when it should be off. And they'll say that my simulation is run, so-and-so a bunch of iterations, but it's not at the time step I need it, the expected time step. A lot of times the solver will just slow down or basically drop the time step more and more and more to basically when you're making no progress. This isn't for free surface where that's basically expected and okay. But, if you turn it on, you're looking at vortex shedding and you turn it on, your time step is probably going to approach 0. So you won't get a lot of results.
Yeah, definitely. Yeah, so I had a customer recently, I think he's here actually, he was getting to, I don't know, thousands of time steps, but it turned out that the simulation itself was very unstable, and the intelligent solution control was dropping the time step to try and make this thing keep running, and it was keeping running, but it wasn't progressing in time. So we had to rethink this and try and stabilize the simulation, rather than and then use a constant time step that we have control over, make it fairly small so that we actually get some progression, but that it's stable enough as well. So our last point is that you can actually sometimes combine modes in one simulation. So the most common example of this is using a steady state flow when you have a simulation where forced convection is the dominant flow pattern. So that means that the heat in the simulation will not vary the flow. It won't affect the flow because the flow is so powerful, and because the flow is so powerful, and yeah, you can just turn that flow off and then start with your heat only analysis, because the two don't affect each other. Yep. So a good example of this, sorry Matt, you go for it.
Just to articulate a little bit, it basically forced convection models. So if you're not looking at, if you're willing to, and you know you can neglect natural convection, and you don't think buoyancy is going to be, have a dominant effect on the flow, this is the perfect application. So a lot of times, my natural convection simulations come out to about 30 inches per second velocity, characteristic speed. So if I'm seeing 1 meter per second or greater, I'm probably okay to assume forced convection.
Yeah, definitely. And then once this steady state flow regime has converged, then you could freeze the flow by disabling flow in the solve dialog and start a transient heat transfer simulation. You could either do this in the same simulation, or for a bit of safety, clone the steady state simulation with saved results and then start the transient heat transfer from there. Because if you mess up on the heat transfer, then at least you've got the starting point still after the steady state flow.
Sounds like you probably learned the hard way, huh?
Yeah, definitely.
I know I
have. So main examples of this is, like we're going to show you in a minute, with oven simulations where you're heating up, or say in a fridge where you're cooling down. But for these to be valid, you need to have forced convection. So you need fans in these ovens operating at a pretty high flow rate that means that natural convection doesn't have an effect in the simulation. Another one is a solar loading analysis. So say if you've got wind loading on the outside of the buildings, and we know that that's forced convection and the natural convection in the simulation won't be affecting it, then you get that steady state flow regime of the wind around the building, and then you apply the solar loading to that. It's not going to be 100% accurate because that wind loading will be changing over time in reality, but it's a good way of speeding up your simulation. And what you could do is say 1 hour of solar loading and then do another steady state flow at a different wind loading, and so on, to try and get your full day of simulation. I mean, that's a big thing to do, but I think it should be possible. So now we're going to go on to an example of a transient simulation. So I've got an animation here of what will hopefully work and not crash PowerPoint, but let's have a look. So opening file, looking good so far. So what we have here is a sort of wing or a spoiler section where we're visualizing the turbulent intensity using traces over the back end of this spoiler. And what I really want to show here is that over time, it's very clear that this is changing, so that there is no steady state solution that's going to come out of this, and that you absolutely need transient solving. So I'll hit play and see what happens.
That looks amazing, man.
There we go. Look at that. Really nice. I've got to say that this wasn't my simulation, but it's a really nice one. And it's nice that it's working in PowerPoint as well. So now we're going to get into some demos of our sort of, it seems like a bit of a festive theme of jacket potatoes and roast turkey, but we'll see how we do. I think both are fairly undercooked. I think my jacket potatoes only got to 50 degrees Celsius, but it should be an interesting learning experience for us. So, Matt, shall I switch over to you take control?
Yep, absolutely. Just give me a minute here, please.
Absolutely. So, I can't actually exit this animation, but Okay, Matt, I can see your screen now.
Good news. Okay. So this was kind of inspired from a custom model that I helped someone work on again about a year ago. They were doing building an industrial oven and looking at how fast things heat up basically. Just to go over, and again, at least for now, I'm following the rules that I actually preached and started at the top with a steady state simulation, which was cool. But basically, down below, I have 4 fans that are blowing up on these semicircle ducts. And each fan has a heater core with 1 kilowatt each. So there's total 4 kilowatts of heating here. This thing's like, I think it's like 3 meters by maybe say 1 or 2. So it's quite large. And yeah, so here's basically the light green are just resistances, which basically, help even out the flow and represent some kind of grates. So I've got 16 turkeys here. And I got the specific heat and conductivity and density of turkey off the internet, which was pretty interesting. And yeah, basically I wanted to see how long it would take for them to heat up. Now, if you're designing furnaces, you're going to want to see that they all heat up at the same time, understand how fast it takes to hit steady state, and look at flow velocity. I mean, ideally you would want uniform flow on all these, although that does not quite happen. In terms of boundary conditions and all, I basically had on the heater cores, I have kilowatt of total heat generation. I put it on a distributed resistance. It's fine to right on the other side of a fan. It's fine to put total heat generation internally on a resistance. And then on the outside, I had a film coefficient to basically just represent a convection coefficient to the room around it. And yeah, we don't have to get into initial conditions because this is steady state. So let's look at results.
What value did you use on your film coefficient, Matt?
I actually didn't model the solid walls. So normally you would put a film coefficient on the outside. So I ended up going with 1 watt per meter square instead of like 5. One's probably a little high. Normally you would put like 5 on the outside, like your metal wall or something like that, insulated wall. Mm-hmm. But anyway, right. So I did my hand calcs in Celsius, but cook with food. So let's see what this is. So probing, this is steady. It hits steady state in 536 iterations. Most of the area where the turkeys are, we're seeing about 375 Fahrenheit, which was my goal. I looked up online, usually cooking at around 350 degrees. If we use the parts calculator on the air volume, so we see average temperature of 186 Celsius, which is good news. That's very warm. It's probably in the probably 370 around there, as we saw here, Fahrenheit. So also I looked at, let me get the planes. I looked at velocity. Basically I'll do inches per second, and I'll probe, and I'm seeing basically my velocities are in the they're well over 50 inches per second, and I'm used to seeing 30 inches per second as a natural convection flow. So it's okay to assume that this is a forced convection problem. Cool. Now, after we ran the natural or steady state model, we have no idea how long it takes to get to this steady state operating point. So if I put turkey's in this oven, and hit go. How long does it take to get to steady state? Is it a minute? Is it 5 hours? I don't know if I need bigger heater cores or better insulation, whatever. So I think my frozen flow transient was just a copy. And then I started doing heat ups with different time steps. So let's switch to one of these. So I looked up online. You basically want, turkey meat at like 180 F, which I think is like 83 degrees Celsius. And then you could call them fully cooked and pull them out of the oven. And of course, you don't want to overcook them. So one kind of cool thing here is that you see there's like uneven distribution of temperature over the turkey. So this would mean some of them would be coming out probably, kind of raw, and some of them would be fully cooked or overcooked. So I guess let me take a couple steps back here. I cloned the steady state simulation. Basically what I did was I cloned the steady state simulation, went to the physics tab, unchecked flow, checked heat transfer, and then chose my time step. So I ran the simulation for an hour, 3,600 seconds, used 300 iterations. 16-second time step. Again, 16 is really big, but because we are not solving the flow, 16 is completely acceptable and fine for transient analysis. Once we freeze the flow, it's almost like we're doing a conduction problem. It's quite easy. But again, I always clone and run with multiple time steps to see how things change. You want basically the coarsest time step that still gives you good results. So for a temperature heat up or temperature decay model, you want to use initial conditions. So I basically did room temperature 20 C on all the air, and then on the turkeys I actually did like refrigerator temperature, so like 40 degrees Fahrenheit. And I really wanted to track the heat up of all the turkeys. I picked 4, and I wanted to see, okay, the center of them, the coldest spot needs to reach 83 degrees Celsius. How long is that going to take? So what I actually ended up doing was putting monitor points in place, which was kind of cool. So I have turkey 1, 2, 3, and 4. If anyone needs a refresher, you put in monitor points by the simulation tab there, go to monitor point. I basically buried them dead center in the turkeys. And then so while running the simulation, so let's jump out. I guess we could touch on convergence plot. The first 500 iterations roughly ran till, or 536, whatever, ran until steady state flow. And then when you freeze the flow, literally all the other residuals are completely flat. So if you look at one, Vx doesn't change at all. We're only doing heat transfer. If you look at the table, it's literally the exact same number, just repeat it. But anyway, so if we look at turkey temperature increase, it's a little okay. So we can see these units are in Celsius. If you don't know what your units are, you can always check the summary file. The turkey was at 500 iterations. It was at I think 5C, and then warmed up. By the time we were at 1 hour, it was only 24.5 degrees Celsius, which is obviously bad. You can always look at the table, and the huge benefit here is you can look at this data while you're running the simulation. It's tabulated. You can save it out in a CSV file and post-process more in Excel. And it's pretty neat. You can see there's my initial conditions, the 5C. Yeah, so I didn't use 4, I used 5. And then you see it starting to heat up. And at 1 hour, it's 24 degrees C. So I need bigger heater cores, basically. Now, touching on inner iterations, you can see here, this column where my mouse is time steps. You see 25, 225, 225, 225. Actually, this is seconds, so 3,600. But regardless, your temperature residual for that monitor point doesn't change. And monitor points are great because they show a physical value where you care about, on exactly what you care about. Yeah, so this was a 16 second time step, and then I did heat up 6, and I used a 32 second. So I doubled it, and now I wanted to see how's that changing. Now, I quickly realized that my turkeys were so cold that it's not even worth post-processing in Excel. But what I kind of wanted to do was plot the temperatures with respect to time in Excel and show that they're trending at the same rate. But I realized it wasn't even worth doing because I need more heat generation in my system. So a cool quick check to do in the post-processing, basically parts calculator. I'll do another one just for the heck of it. Grab one of the turkeys, click summary part, calculate, and then you can go to the decision center and look at the average, min, and max temperature on this body between my 2 different scenarios, which have 2 different time steps. So let's do that. All right, let's only focus on the rightmost, or the 2 rightmost columns. So heat up 5 and heat up 6. So again, heat up 5 is using a time step of 16 seconds, while heat up 6 is using a time step of 32. But if you look at the average temperatures, they're identical, which I thought was pretty phenomenal. Honestly, that made me think, well, I could probably double my time step again and just keep doing this. And
that's really cool. That's what we were saying about having a larger time step for a heat only simulation, and Matt's completely proved this, and it's really nice to see that you could get a massive speed up in your simulation time using a bigger time step.
Yeah, I mean, to be honest, I started with a 1 second time step, which, in hindsight was foolish, but that's why I stopped the simulation early, and, I had to rehash a couple of these things, but
well, that's why your turkey's undercooked, isn't it?
Yeah. So again, no change in average temperature. You can post-process the data using monitor points. Yeah. Any questions, David?
No, it looks really good.
Cool. Safe to say I probably shouldn't be designing ovens, though. All right. Do you have your model open? You want to take a look at it?
Yeah, I've got it open. Yeah, we'll take a little look. It's a very similar idea to what Matt has done, but I'll show you what I've done, because it's nice just to have a look at another example just to really get it secured in your mind. So, can you see my screen, Matt?
Yes, I can.
Awesome. So I went with a bit more of a traditional oven.
Nice.
Literally modeling the oven in my house. Found something on GrabCAD, so thank you very much if you ever see this webinar, whoever designed it. Inside we've got a couple of strangely shaped jacket potatoes. Here we are. And an internal fan on the back. So pretty similar to how your traditional household oven works. And I'll just show you where we've got these 2 heating plates. So I chucked some boundary conditions on these heating plates. Literally opened the oven in my house to find out what the wattage was on these things.
That's awesome. They're realistic.
But yeah, well, the thing is, I couldn't insulate my oven as in reality. So I think what the problem is, what we've got is my film coefficients may be slightly too high. So we've got straight to steel, which is pretty conductive, obviously, and then out with a film coefficient. So I think a lot of the heat is actually being driven out of the oven.
Yeah.
Whereas in reality, you're having big insulatory materials on the inside.
Yeah, you have like some kind of wool insulator. Yep.
Exactly. So then this was my steady state simulation, just running flow only. We'll have a little look at the results. So we just got flow coming out of the fan, circulating nicely through the oven. And then you can see there's the potato. And what you do at this point, once you've got a converged steady state solution, so just to recap on what Matt did, so you guys really get it in your minds, you go here, you go clone, and you include the mesh with the results, and hit OK. And then you can start your transient simulation.
Yeah, good idea kind of stepping through that, David. Now, one other thing, you probably ran into it. I know I did. When you switch from steady state to transient, naturally intelligent solution control is left on. So you got to remember to go in and deselect that.
Exactly. And when you're in there, so where's your solution control? You can see this is disabled, and also the automatic convergence assessment is disabled just in case you were going to use the intelligent solution control to stabilize your simulation. Make sure you got the auto convergence assessment turned off. So now we're in the transient analysis, and the same with Matt is I started with a pretty small time step, expecting to get to a steady state solution fairly quickly, but actually I simulated simulation time with time steps or time to completion of 2 hours and 40 minutes. So you would expect your jack potato to be done by that time. However, we're in our simulation here in the results, and here is the final result. Oh, hang on. So what we'll do, I'll run you through how you animate a transient simulation, because I've had a few questions on that recently. You right-click on the canvas, head to animation, and I want to be animating the temperature so that I can see the potato and the fan and everything. And you see here all the saved time steps, and that is defined by the save intervals in the solve dialog. And you can see that I've run through here, and then it's not best practice, but to speed things on, to try and get my potatoes up to temperature, I changed the time step up to I changed the time step, and I also changed the save interval, as I noticed my folders were getting much too large, so I went to a 5-minute save interval instead. And we can animate that. So we select all there, hit animate, and hopefully we'll see from the bottom. I'll just see if we can. That's the maximum range. So I really didn't get very hot at all, but here we go. And you can see the plate on the bottom is giving out a lot more heat for some reason. I don't know if that's to do with the flow field around the top one, but I suspect so. Matt, can you think of any reasons why the bottom plate would be heating up a lot more?
Is the fan hitting the bottom plate first? No, it'd be hitting the top.
No, it's hitting the top. I think the fan is really taking the heat off the top heating plate really quickly.
Yeah, that's probably it. There's no obstruction there.
No. And we see we're stepping through here, and you see so I left these velocity vectors on so you could see that the flow is not changing because we froze it by only transiently simulating the heat transfer. And what we'll do, I'll skip to the end. You can go up here if you want. Go to the last time step. Aha, here are my higher temperatures. Nice. So on my final time step, after 2 hours and 40 minutes of cooking, we can go in and you can see down there that the middle of the potato is at about, if you see down there on the Matt, can you see that, my value in the bottom panel?
Yeah, it's 65C.
Perfect. Yeah. So 65C inside the potato. It's not bad, but I did check on eggheadforum.com and there was vicious discussion about what was the perfect roast potato temperature for internally, and it was 90 degrees. So sadly, I missed it, but maybe next time.
Right. And, once you run one of these, I mean, you can basically, mess with your exterior walls and film coefficient and benchmark it with time. Once you do that, you have a verified model, and then can go keep the same fill coefficients and walls, and then go run more tests.
Okay, great. So that's all I have to show for you. Hopefully you've got good impression of how to set up one of these heat up, cool down simulations. I'll just head back to the PowerPoint.
Awesome, David. Nice job. All right, we only have 2 minutes left. If anybody has any questions, someone was asking if these webinars are filmed and posted. Yes, they are. We basically upload them to YouTube and put the slide deck and the share files on a box folder. We then send out an email to everybody that registered for the webinar with a link to both. So nice job, David. It was cool to see the residential application of the oven. I had the more conveyor belt version.
Yeah, I'm not sure there are many other people simulating residential items, but you never know.
Sure, cool stuff. Someone's got that job, so.
Yeah.
All right, thanks, guys. Bye.